Yes, so my name is Johan, and together with my colleagues, we have worked on uncertainty modeling and its application in diarization. Okay, so why we are interested in this uncertainty modeling is that if we think of the typical diarization process, we take some recording and we split it into segments, and then we extract embeddings for each of them, and we try to cluster the embeddings so that segments from the same speaker ends up in the same cluster. And the embeddings that we extract, they depend on speaker identity, but they also depend on factors such as noise, duration, or phonetic contact. So it is a speaker embedding, but it also has some additional randomness, which we can call the uncertainty. So we argue that this uncertainty is something that we should try to model and accurately try to incorporate in our models. So for example, in diarization, that means that some uncertain embeddings will affect the speaker model that results in the diarization process less than the certain embeddings. So before, we have already worked on this topic a bit, and we tried to estimate uncertainty in embeddings based on a neural network. And this neural network, it took as input the statistics from a pooling layer in embedding extractor, and also the embedding itself. We were for this task, we needed a kind of new training objective, because we need something that is discriminative, because the model is not a complete generative model. And also we need something that trains the model for open set speaker kind of recognition. So we cannot really use multi-class cross entropy or something like that. So the objective that we used was this, that we can call the tuple-based objective, where a training example are segments. So I show there 8 segments, U1 to U8, and the task of the model is to cluster these. So for example, it may say that all the first 3 are from one speaker and the following 5 are from another speaker, or it may say that segment 4 and 6 are from one speaker, segment 1 and 5 is from another, and so on. So basically, there are many partitions like that. From 8 speakers, from 8 segments, you can form around 4,000 partitions. So the task of the model is to say which of the partition is the correct one. So this is an objective that we used in the past and in some of the work here as well. And we used embedding, we clustered embedding just based on agglomerative hierarchical clustering. So in the workshop, we worked on incorporate the embedding uncertainty also in the VBX recipe or model. And we try to improve the estimation of uncertainty. And we also worked on a new kind of diarization method based on transformers. So first, regarding the incorporation of uncertainty in VBX. So VBX is a probabilistic model based on HMM. So you have, for example, now you are in you have some embedding, and it's has been assigned to speaker 1. Then we have a probability that the next segment will be from another speaker, or we can say it could be the same speaker, and so on, right? And the speakers, we have hidden variables in this model, which represent the assignment of segments to speakers, called Z in that little equation there. And this is what we are trying to find, and we do that by variational Bayes inference. So this is a model that has been we have been used for quite some time, and what we added here now is to before we used it among other stuff for modeling X vectors as observations, but now we want to model X vectors or some embedding along with some uncertainty. So the observations are now kind of probability distributions instead. So we extended that, and we did some experiment with X vectors where the uncertainty is estimated as in our previous work. And we also did on I-vectors, where you have kind of, from the model, we have already a natural, you obtain directly a estimate of the uncertainty of the I-vector. So it's clear here, first of all, if we look at the upper part of the results, X-vector, so these are without uncertainty used in the VBX. And here we see that X-vectors is quite a bit better than I-vectors. And these results here is actually quite good compared to some results we have seen before. So actually VBX can be quite well, perform quite well. And we should maybe also notice that here is not, this method is not really designed to deal with overlapped speech as in the moment, although we consider to extend it for that maybe in future. Then if we look at the I-vector result for I-vector, we see also that using the uncertainty helps quite a bit. We can compare the two orange lines or the two blue lines. So it does help. However, we could not get at this stage any improvement of by using the uncertainty of X vectors, which is a bit surprising. It's probably we have done some mistake or overlooked something, because we had quite good improvements of using uncertainty estimation for AHC. So this is still something that we would have to look more into later on. So now, a second experiment with VB was to, so the thing is that the result of the VBX depends on how you initialize the initialization you give to it. So attempting approach there would be to do something like, okay, we select, for example, 20 random clustering hypotheses, and we apply VB to each of them, and then we check the score, because the VBX also outputs some kind of score, how good the results is, let's say, and we could select some based on this score, the one that gives the best score. But this never worked for us in the past, but we see now that when we do include uncertainty estimation in the embeddings, this approach actually works. And this is nice because it suggests that we now have a better kind of more accurate modeling of the embeddings. So now I'm leaving the VBX and just talk a little bit briefly on the how to estimate uncertainty, because I said that we estimated the uncertainty using a neural network, which took as input the statistics from the pooling. So that's, and also the counts, the zero order statistics. And this is quite reasonable because what comes out of the pooling is basically sample mean and sample standard deviation. And the variance, as probably we most know, the variance of sample mean depends on the standard deviation of the input and the number of samples, if we assume identical independent distributed data. So actually the uncertainty, and then the embedding is just, and the same goes actually for the variance of sample variance. It's just a little bit more complicated formula. So in principle, since the embedding is just affine transformation of this pooling output, we know really the uncertainty related to duration based on this. So it's actually quite reasonable to do what we did in order to estimate the uncertainty coming from the fact that we are using finite duration segments. However, it's maybe not so reasonable to assume that uncertainty coming from noise or phonetic content and so on could be estimated based on this input, because, for example, very noisy data tends to make MFCC more identical, which would make the second order statistics in pooling layer quite small, which would actually suggest a low uncertainty in the embedding. So here, instead, we started to look to do something to estimate uncertainty using something similar to how we actually produce the embedding. So we have some convolutional neural network, and the frame-wise output is then eventually forced to be positive because we think that it should represent the amount of useful information in the frame. And finally, we do some summation over these frames to get what we call the precision, which would be the inverse of the uncertainty. This we actually, unfortunately, we don't have this to give any improvement. We didn't try it in combination with the previous method, but on its own, we haven't managed to improve on what we had before. But I still think that we should get something from it with a bit more experimentation. We actually just started this. So, and finally, let me go also to the diarization we did using transformers. And this is a work inspired by self-attention mechanism used in diarization in some other diarization works, and also some self-supervised works. So we use a self-supervised method called passe to extract features, basically. And these are features that represent, basically it's a very generic representation of speech data. And then we applied diarization. We did diarization by using kind of multi-layer self-attention mechanism. So for the passe, that one process quite like high, like very short segments, and we will normally, and we in addition applied on the output of that one convolutional neural network with some reasonably high stride to kind of get a little bit fewer frames or fewer segments, let's say, representations per second. So in the end, we had something like 5 frames per second, which will be the input to the transformer network. And this is a transformer network where we, at least in the final version, shared the projections between the keys and queries. And the similarity between the keys and queries was measured by cosine distance. And finally, this network, let me go to the next one. So finally, the transformer, on the final layer, we compare all the embeddings with dot product, and therefore we get a kind of similarity matrix for each pair of segments. And this one, we will apply binary cross entropy as objective in training, where we say it should output the probability 1 if it's the same, if the same speaker exists in the 2 segments. There could be more than 1 speaker, but if the same speaker is there, it should be 1, otherwise 0. And in testing, we do clustering based on this infinity matrix. And we also had, a multi-head version of this. So this here in these experiments, we were looking as baseline as using the output from the passe plus this convolutional network for reducing the frame rate. And that alone gave something like 46% or 46 with overlap, or 41% with no overlap. And with the best self-attention or transform-based model, we get around 29 or 20% diarization error rate. So basically, this means that what the transformer does, it's that it kind of refines the embeddings in each layer. So each layer, it becomes a little bit more representative for the speaker identity. Yeah. And what we will continue with is more analysis and work on these methods, because a lot of these things have just started. And we are also thinking much about other training objectives. It's something that we kind of studied and discussed quite a lot during the workshop, but we didn't yet conclude what really is the best thing to do there. And we studied until now mainly methods that do not deal with overlap speech. It has not been our primary focus, but we will extend also our methods to deal with this in future work. So that was all from me.
Thank you for the talk. I think given the time, I think if people, audience have time, probably they can ask in the chat, and you can answer for the chat.
Yes, of course.
Yes, so Johan, there's a question in the chat from Prachi. She wants a bit more detail about downmerge. If you could answer it there, that would be great.
Sorry, yeah. I thought that's basically, so I mentioned that one thing was the using, let's say, 20 random initializations. Downmerging, we also have several initializations, but they are done in the way, if I say it wrong, I hope that someone corrects me, but we do the AHC in the normal way, and then when we at some point stop the clustering because of some threshold, we will continue to check. That will be our first initialization, and then we check all the following clusterings. If we do one more clustering step, take that as output, another one until everything is clustered, and so we use each of those outputs as initialization.
Yeah. Johan, please continue in the Q&A box.
Yeah. Okay, then let's welcome, and thanks again for the great talk, and let's welcome to our last presentation from Roshan Sharma.